Hello and welcome to the video on frequently asked questions from week 4 in the course Statistics for Data Science 2. So this is the first question from activity questions 4.2. Which of the following options are correct for a discrete random variable x? So multiple options can be correct. So if you see, essentially in all of the options we have to choose what will be the difference in the CDF, how will it represent, which probability it will represent. So this is the CDF. Okay, the CDF of x at b minus CDF of x at a, what will it represent? That we have to answer here. As you know, the CDF of any random variable at any point, suppose it's b, it will represent the probability that x will take value less than or equal to b. It's including the point b. That's the important thing here. Similarly, at any other point a, it will represent the probability that x will take value less than or equal to a, including a. Now, if we subtract the CDF of b minus CDF at a, it means first of all we have the probability of occurrence of all the points up to b, and from that we are subtracting the probability of occurrence of all the points up to a including a. It means it will be the probability of occurrence of points between a and b, but we are not including a because we have subtracted it, because in this CDF at a, it includes the point also a. So we can understand it through a simple example. So suppose x was a random variable which was simply uniform in the discrete range 1, 2, 3, 4, 5. So I am not concerned with the exact probabilities, but in a general way, if we consider the difference of the CDF at 5 and the CDF at 3, what will it represent? It will represent the probability that x will take values between 3 and 5, but we are including 5, but we are not including 3 because we have subtracted it here. Okay, CDF includes that point also. So from this simple example, you can extend it to any general case and it will correspond to the second option. So second choice is the correct one. In the second question from the same activity 4.2, we have been given the cumulative distribution function of a discrete random variable x. Okay, and we have to find the range of x. So the range of x will be the set of all points where for which x takes some value with some probability, right? And if some value is taken with 0 probability, we will not include that point in the range of x. So what we can do, we can check all the points for which there is some jump in the CDF. So that we have to find out. So it will be better if we see this visually. So let's try to do this. So on the x-axis we are plotting all the values, and here is our CDF that's given already. So we can mark all the points 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7 and 8. So it's 0 before 0. So we will do it in another color. So before 0, it's 0. But at 0, it moves up. And we see that it's at the point 0.29. Right? And it's 0.29 up to 1. Before 1, I will say. That's before 1. And exactly at 1, there is a jump in the CDF and it becomes 0.68. So suppose this is the point 0.68. So again, here no value is taken and here also no value is taken. So, but here there is a value taken by the CDF and it's 0.68. Then again up to 4, this remains constant 0.68. But exactly at 4, it does not take value at 4. There is some another curve that starts from here. So at 4, we see that it has become 0.88. 0.88. So at this point it becomes 0.88. And from 4 to 8, 4 to 8, before 8 it is 0.88. But exactly at the point 8, what happens? It becomes 1. So there is a rise in the CDF by 0.12. So at this point, we'll say this point. After this, it becomes 1. It is equal to 1. That is the property of the CDF, as we already know. So what are the points at which we see the jumps? And wherever we see the jump, it means there is a non-zero probability of observing that value for the random variable. So we see the jump at this point 1. We are not concerned with how much is the jump, but at least it should be non-zero. That's the main point. So the range of x we can consider as all the points where there is a jump. Range of x as, first of all, there is a jump at 0, so 0 will be one of the points. Then at 1 there is a jump, then at 4, then at 8. So 0, 1, 4, at are all the points where there is a jump, and at other points there is no jump, so there is 0 probability for them. So the range of x will be this 0, 1, 4, 8, set of 0, 1, 4, 8. So fourth one is the correct option. The third question is based on the same data that we are given, but here we have to calculate the probability that x will take value 4. So as we know, if we have been given the CDF or the cumulative distribution function for a discrete random variable, then for calculating the probability that it will take a certain value at any point is represented by the amount of jump that CDF function takes for that random variable at that point. So here we have been asked what is the probability that it will take value 4, that will correspond to the amount of jump that CDF function takes. So it will represent this, the amount of jump. So here we see that it's 0.20. It means that the probability that x will take value 4, it is equal to 0.20. The fourth question is also based on the same data, but here we have to calculate some conditional probability. So we have to calculate the probability that x will take value 8 given x has taken value greater than or equal to 4. So as you know, this conditional probability can be written as the joint of both the events and divided by the marginal probability of the event on which it is conditioned. So the probability that x will take value 8 and x takes value greater than equal to 4. So this is the joint probability divided by the marginal probability of the event on which it is conditioned. So it is x greater than equal to 4. So first of all, coming to the joint probability that is there in the numerator, what will be the probability? So probability that x equals 8 and x is greater than 4. So what are the values of x for which this probability corresponds to? So as we know, the range of x is just 0, 1, 4, 8. So if x has value greater than or equal to 4 and x has taken value 8, it means the joint of them will just be the probability that x will take value 8. So this was about the joint probability. What about this marginal probability? Probability that x will be greater than or equal to 4. So what are all the possible values of x does this correspond to? So x is greater than or equal to 4. It means x can take values 4 plus x can take value 8, because after 4 there are only 2 values that can be taken, including 4. The probability at x equals 4 that we already calculated, it is a 0.20. What about the probability at x equals 8? So as we saw here, the amount of jump that was there at this point x equals 8, it was 0.12. So it will represent the probability with which this value x equals 8 is taken. So it will be 0.12. So this probability is just 0.32. So now we can put these values and get the answer. The probability that x equals 8 that we already saw, it was 0.12 in the numerator divided by 0.32. So which if we calculate 0.32 12 divided by 0 point, it's equal to 0.375. 0.375. So this is the required condition probability that we have been asked for. In this question, we have been given the cumulative distribution function of a discrete random variable x, and we have to define another random variable y, which is equal to 2x squared plus 1. So it is a function of x, and we have to find the PMF of y. So because y is a function of x, it will take values depending on what values does x take. So first of all, we need to know what is the range of x, or what are the values that x can take. And for knowing the range of x, we need to find out all the values where this CDF has a jump, or this random variable takes some value with non-zero probability. So for finding the range of x, so it will be better if we draw the graph for it, the CDF, so that we are able to visually see this. So x, and here we are representing the CDF at the point. So what are the points that we have to consider? -1 and -2. 1 and 2. So before -2, we will take a different color here. Before -2, the CDF function is 0. It's 0 before -2, but exactly at -2, there is a jump in the function, and it suddenly becomes 0.15. So I'm not taking into account the scale, so don't care about that. So at exactly at -2, there is a jump by 0.15, and we find the function taking value 0.15. Now this value is constant up to -1, not up to -1, but before -1. But exactly at -1, there is again a jump, and it becomes 35, 0.35. So it takes this value at this point, and this value remains constant just before 1. But exactly at 1, there is again a jump, and it becomes 0.75. 0.75, yeah. And it similarly remains constant up to 2, or just before 2, and then at 2 there is a jump, and it becomes 1. It becomes 1, and after 1, or sorry, after 2, there is no jump, and it remains constant. So we have to see at which points there is a jump, and those points will correspond to the values that the random variable x can take with non-zero probabilities. So range of x will be the set of all points where there is a jump. So first jump we see at -2, then there is a jump at -1, then we see a jump at 1, and then 2. So these are all the points which represents the range of x. Now we need to find the PMF of y, but before that we need to find out what are all the values that y can take. So y is a function of x, 2x squared plus 1. So we will try to put each value of x and try to see what are all the distinct values of y that we can get. That will represent the range of y. So you can see here that if we put -1 or 1, the y will take the same value, because x squared will become positive. So if we put -1 or +1, it will become 2 times 1 plus 1, that is 3. And when we put, so when x equals -1 or 1, this is the first case. And in the second case, when we put x equals -2 or 2, y becomes 2 times 2 4, and 4 times 2 8, plus 1 9. Y takes value 9. So it means we can draw a PMF table for y, and here we can write the PMF for y. So y can take values 3 and 9. So as you know, when calculating the PMF of any function of another random variable, what we do? So we will write this as the probability that y taking value 3. Now when can it happen? So we don't know the distribution of y, but we know the distribution of x, and we can represent it in terms of the distribution of x. So y equals 3 when x takes value either -1 or x takes value 1. So it will both the probabilities will be added. So it is clearly 0.20. And at +1, what amount of jump is there? So it is clearly 0.40. So it means we will add 0.20 plus 0.40. So the probability that y will take value 3, it will be 0.60. We can put it here. Then for calculating the probability that y will take value 9, similarly, it will correspond to x taking values -2 or x taking value +2. So at -2, we will have to say how much is the jump, and then at +2 also, and we will add both of these probabilities. So at -2, the jump is 0.15, and at +2, the jump in the CDF is 0.25. Here you can see. So x equals 2, x takes value 2 with probability 0.25. So it is equal to 0.40. So this is the PMF table for y. So it corresponds to the third option. In question number 6, we have been given a discrete random variable x, which have a CDF fx. Assume that y equals x minus mu divided by sigma, where mu and sigma are the mean and the standard deviations of x respectively. If y is the distribution function of y, which of the following options is true? So basically we have to find out the cumulative distribution function of y. So if y at some small y, that's what we have to calculate. So as you know, the CDF of y is equal to the probability that the random variable y will take values less than or equal to the value small y at which we are calculating the CDF. But y is given as x minus mu divided by sigma. So we are just exploiting the relationship between y and x here. So we can write y equals x minus mu divided by sigma, which would be less than or equal to small y. Now we can simplify, keep the x on the left side and move all the terms mu and sigma on the right side. Then we will have x less than or equal to sigma y plus mu. Now what does this probability represents? This probability that x will take values less than or equal to some value, doesn't matter what value it is definitely can be it can definitely be expressed as the CDF of x at this point, sigma y plus mu. So this is the CDF of y. So what we have done essentially here is we have converted the problem of finding the CDF of y in terms of the problem of finding the CDF of x, CDF at some value of x. So the option corresponding to this is the second one. In this question, we have been given a random variable x, which follows a geometric distribution with parameter p. We have to find the cumulative distribution function of x, or the CDF of x. So we have been given x, which is geometric with parameter p, and we have to find CDF of this random variable, suppose at some point small k. This is what. So as you know, the CDF of any random variable at any point k, it is nothing but the probability that x will take value less than or equal to that small k. So if we add all of the values up to k, all of the probability values up to k, then we will get the CDF. So it means probability that x will take value 1, because a geometric random variable always takes values 1 or greater. So we will add x takes value 2 and so on up to probability that x will take value small k. So this is the CDF. So calculating all of this, we will need the PMF of x. So small fx at k, the probability that a geometric random variable will take value k it is equal to 1 minus p raised to the power k minus 1 times p. So this geometric random variable represents the probability that you will get a success in the kth trial. So k minus 1 times you got failure, and then at the kth trial you get success. So this we have the PMF of the geometric random variable, and we can use this to calculate this CDF. So the CDF of x at some small k, it can be written as probability that x equals 1 plus probability that x equals 2, and all of this being added up to k, and we'll add the PMF values. So when we put x equals 1, it becomes just p. When we put x equals 2, the PMF of the geometric random variable, it becomes 1 minus p times p, and so on. It's being added 1 minus p raised to the power k minus 1 times p. As you can clearly see here, this is clearly the sum of k terms of a geometric progression. So let's recall geometric progression. Geometric progression, or GP, if we have a geometric progression with the first term as a and common ratio as r, then the sum of n terms is given by a times 1 minus r raised to the power n divided by 1 minus r. This holds true when the common ratio is less than 1, and that's true for this our case, because in our case the first term is a and the common ratio is 1 minus p. So 1 minus p would be less than 1, so we are using this version of the formula, 1 minus r. So we know what are the first terms and common ratio in our geometric progression is. The first term is clearly p, and the common ratio is 1 minus p. 1 minus p is being multiplied each time. So r, that is 1 minus p, raised to the power, how many terms we are adding? So we are adding the first k terms. So n equals k in this case. So raised to the power k divided by 1 minus r. In our case, the common ratio is 1 minus p. So the denominator will just become p, and it will cancel out the p in the numerator. So finally, we will have 1 minus p raised to the power k. So this is the CDF value at some point small k for a geometric random variable. And for what values of k this CDF function is applicable? So it will be applicable for all of the values which the random variable x can take, a geometric random variable. So as you know, it cannot take values less than or equal to 0. So before 0, CDF will be 0, and after 1, it will take some values. So clearly, second option is the correct choice. Here we have been given a CDF. Consider the following CDF of a random variable x and answer the questions 8, 9 and 10. So based on this CDF, there are 3 questions. So first question says find the range of x. So as you know, the range of x will consist of all the points which x can take with non-zero probabilities. And at those points, if you see the CDF or graph of the CDF function of x, at those points you will find jump in the CDF because it is a discrete random variable. So before minus 1, you can see that the CDF function, the value of the CDF function is equal to 0 here. But exactly at minus 1, there is a jump, and by what amount it jumps? It jumps by 0.2. Right? So it means minus 1 is one of the values that is taken by x. So here I will write the range of x. So the first value that x can take is minus 1. The second jump we see at plus 1. How much is the jump? The jump is by 0.4. So it means plus 1 is the another value that is taken by x with a non-zero probability. And the next jump we see at plus 2. And how much is the jump? Jump is by 0.4. So 2. And after that, the CDF function remains constant. So we can say that there are only 3 points where there is a jump in the CDF function for x. So only these values minus 1, 1 and 2 are taken with non-zero probabilities. It means the range of x is minus 1, 1 and 2. So the second option is the correct choice. Now coming to the 9th question, we have to calculate the probability that x will take value 0 plus probability that x will take value 1. So this is the ninth question. Probability that x will take value 0 plus probability that x will take value 1. So what is the probability that x will take value 0? So clearly we will see how much is the jump at that point, and the amount of jump at the point where we want to calculate the probability will represent the probability of that point taking the value, okay, or x takes that value. What is the probability of that? At 0 we see that there is no jump, it is constant. It means the probability is 0, and also 0 does not fall in the range of x, so 0 is taken with 0 probability. What about 1? So at 1 we already saw there was a jump, and how much was the jump? It was 0.4. So 0.4 is the probability with which this value is taken. So if we calculate the total, it will be 0.4. So the answer for this is 0.4. Ninth question. Coming to the 10th one, it is asking probability that x will take value less than equal to 1.5. So we'll have to consider all the points before 1.5 where there is a jump, and we'll need to add all the probabilities, right? So it is clearly the probability that our random variable will take value less than equal to 1.5. So 1.5 is at this point. So exactly at 1.5 there is no jump. So what are all the possible values that x can take before 1.5? So we saw that the only values that can be taken are x equals 1 because there is jump at 1, and before that there is a jump at x equals -1, right? So there are two jumps before 1.5 that we have to add the probabilities for. And the jump at +1 it is 0.4, while the jump at -1 it is 0.2. So if we add total it will become 0.6. This is question number 2 from the activity questions 4.3. Here we have been given some functions and their graphs, and we have been asked whether they are valid cumulative distribution functions. So as we know, for any function to be a valid cumulative distribution function or a CDF is that it should satisfy a few properties. The first property says that it should be a non-decreasing function. Second criteria is that as x approaches -infinity, the CDF should go to 0. Third, as x approaches +infinity, the CDF approaches 1. So these are the three criteria that we evaluate for any function for it to be a cumulative distribution function. So let's come to the first graph. So for the first graph, the first condition that we will check is the first condition. It should be a non-decreasing function. Yes, it is a non-decreasing function. The second condition says that when we approach -infinity, then the value of the function should go to 0. So as we see here that at x equals 0 only, this cumulative distribution function has become 0, and after a certain point it has become constant at 1. So this is the third criteria. So the first graph is satisfying all the three criteria for being a cumulative distribution function. So yes, we can say that it is a valid cumulative distribution function. What about the second one? For this also we will check first the first condition. The first condition says that it should be a non-decreasing function. So but here we can observe that first the value of the function goes to 0.6, then it again comes back to 0.3. It's not exactly 0.3, but after at whatever point this value 0.6 was obtained, after that the value of the function decreases and then further it increases, although it follows all the other conditions that as we go -infinity it should become 0, and as we go to +infinity it should be a constant that is equal to 1. Those conditions are followed, but it is a non-decreasing function, so it cannot be a valid cumulative distribution function. What about the third one? Third one, yes, it is a non-decreasing function. And checking the second and third conditions, so when x approaches -infinity, so yeah, it has already become 0 at this point, and as x approaches +infinity, yeah, it has been a constant, so it can be also a valid cumulative distribution function. What about the fourth one? Let's check the first condition for this also. So it should be non-decreasing, but it is decreasing. So we can conclude that it is not a valid cumulative distribution function. So only first and third options are correct. This is the question number 2 from activity questions 4.4. Which of the following functions cannot represent the CDF of a continuous random variable? And it's given that all the functions are non-decreasing functions. So as we discussed in the previous question, there were some conditions that were required for a function to be a valid CDF. The first condition was that it should be a non-decreasing function. Non-decreasing. The second was that as x approaches minus infinity, the value of the function should approach to 0. And the third condition was that as x approaches plus infinity, the value of the function should approach to 1. So these were the three conditions that was required for any function to be a valid CDF. But for a function to be a valid CDF of a continuous random variable, so it's generally true for discrete random variables, but for continuous random variables there are two more conditions that are required. Conditions for continuous. The first condition says that the function should have no jumps or steps. Shouldn't have any jump or steps. So this was allowed for the discrete random variable, and the amount of jump represented the probability with which that value is taken at the point where there was jump. But for the continuous case, it is not allowed. As a result of being no jump or steps, the value of the probability that x takes any particular value, it is equal to 0. So these are the two conditions. So for checking whether any of these functions are representing CDF of a continuous random variable, we need to check for these two conditions. So let's come to the first option. So as we can observe here, this CDF function is defined in pieces. So there are different pieces. The first piece we can see it's 0 before -2. So it is like constant before -2. It's like a constant function. After that, it becomes a line. So it's a line with the slope 0.5/3. Then again, it's a constant function 0.7 from 1 to 2. Then again, it becomes a line 0.3 with 0.3 slope. And then it's a constant function after x equals 3. And it's equal to 1. So as you can observe here, whenever the piece of the function, whenever we are graphing it, it is a line or it is a constant function, then there is no chance that it will have any jumps or steps, right? Because if you have any continuous function like a line, like a constant function, they don't have jumps, any jumps. But the chance of having a jump is at the interfaces of the pieces. So what does it mean? It means that whenever the definition of the function is changing from one piece to another, there is a possibility that there might be a difference in the values taken by the function, and that might cause the function to have jumps or steps. So let's try to graph this situation here. So suppose this is -2 here, and here it's 1, it's 2, and it's 3. So before -2, it's equal to 0. It's 0. Okay. Exactly at -2 it becomes, so we will put the value -2 here, and it will be equal to -1.0 plus 1.4, so 0.4/3. So it will be 0.13. So before -2 it was 0, but exactly at the point -2 it becomes 0.13. Suppose this is 0.13. So it takes value exactly at -2, which is different from 0. So it takes value 0.13. And after that it becomes a line with the slope 0.5/3. So suppose this becomes this line. We should not care how it looks later, because at this point only we have found that there is a jump. So there should not be any jumps in the function, but here we found that it has a jump at the start itself, and you will find that later also it has a jump. So when it goes from this piece to this piece, it has a jump. So at x approaches 1, what should this line approach to, so that it becomes continuous? So as you might observe here, when you put x equals 1 here, what will it become? 1/3, and 0.5 plus 1.4, that will be 1.9. So it will be 0.666, so 0.67. So its value approaches the value of this line approaches 0.67 as x approaches 1. But next part of the function starts with 0.7. So you can see that again there is a jump of 0.03. So you can observe that this function has a lot of jumps, so it cannot represent the CDF of a continuous random variable. Coming to the second option, it's almost the same as the first option, but only difference is that in place of 0.5 here we have put 0.7. So let's try to draw now for the second option. So again, before -2 it's 0, 1, 2, before -2 it's 0. Exactly at -2, what is its value? So if we calculate 0.7 times -2, it will be -1.4 plus 1.4. It will be 0. So this function, this line starts with 0. So this was 0. Before -2 it was 0. So when there is a transition from this piece to this piece, the next piece of the function starts from 0 and becomes a line with the slope 0.7 by 3 and goes on further. So yeah, it's clear that it has no jump at this interface. Let's come to the second interface, because we should check it for all the interfaces, right? So whenever a function has one jump, it means it cannot represent the CDF of a continuous random variable. But having just one continuous transition from one piece of the function to another is not enough, right? We should check it for all the transitions. So the first transition we have checked. Now let's check for the second transition. So as x approaches 1, what does the value of the function, this line, becomes? So as x approaches 1, you can see that it will become 2.1 divided by 3. So 2.1 divided by 3, which will become 0.7. So yeah, it was a line and it became 0.7 at the end when x approaches 1. No, sorry. Here it should be as this line approaches x equals 1, it becomes equal to 0.7. So next part of the function, it becomes a constant function from 1 to 2. So you can see that there is no jump. Okay, this line was coming at the end as x approached 1, its value became 0.7, and the next piece of the function picked it up from 0.7, so there was no jump. But now let's check it for the third transition. So as x approaches 2, it will always be 0.7, right? So for it to be continuous, this piece of the function should also pick it up from 0.7. So at x equals 2, what is the value of this piece? We need to check it. So 0.3 times 2 plus 0.1, which will be 0.7. So it means this is again a line with the slope 0.3. So at x equals 2, it will pick it up from the value of the function at 0.7, and it will again become a line up to x equals 3. So it becomes 1 here, right? So this was a line before and it becomes 1 after 3. But we need to check if this transition is continuous. So as x approaches 3, it should become equal to 1. Okay, because suppose this was only up to this and this was only up to this, and next piece of the function, so and next piece of the function started from here, then it will not be continuous, right? It has a jump. So but this line is such that when x approaches 3, so then we will have 0.3 times 3 plus 0.1, so it will become 1. So this line, the last the second last piece of the function is such that when x approaches 3, it becomes equal to 1, and after that also it becomes equal to 1 because it is CDF. So it means each transition of the function, whenever the function is transitioning from one piece to another, it is always continuous. It is not discontinuous, or it does not have any jump or steps at any point. So it can definitely represent the CDF of a continuous random variable. Sorry, it cannot represent. So it cannot represent a valid CDF of a continuous random variable. Now let's check it for the third function. So the first transition you see at this point. So even without drawing the graph, I hope you can imagine it. Before x equals 0, it is 0. Exactly at 0, what does happen? So at x equals 0, we will put it becomes some kind of a curve. We don't know what kind of a curve it is, doesn't matter. But at x equals 0, what's the value of this curve or this piece? So when we put x equals 0, it will become which is equal to 1. So it means it is equal to, so 1 by 2 part this becomes 0, and finally we are left with 1 by 4. So it means that at x equals 0 there is jump, right? Before 0 there was the function of the value was 0, but exactly at 0 it becomes 1 by 4. How can that be possible? That can be possible only when there is a jump or a step. So we can conclude that it cannot represent the CDF of a continuous random variable. Coming to the fourth option, we see that there are just two pieces of this CDF function. So let's try to graph this. So this is 0. So before 0, we see that the function takes value 0. CDF function takes value 0. So we can draw it with a different color. And after 0, if you see, it is defined by this expression. So if you graph it, you will find it is something like this. It will gradually increase and it will become an asymptote to y equals half. An asymptote basically means that it will never reach the value half, but it will be very close to half. So it will go up to infinity, and at infinity it will become equal to half. So if you put infinity in this expression, so it will become half times 1 minus e raised to the power minus infinity, and that is just equal to half. So at infinity it will become half. But remember the conditions required for a function to be a CDF function. It has to become 1 when the value goes to infinity. But when we put x equals infinity, it just becomes half. It is not becoming 1, right? So other conditions are fulfilled, but only this condition, condition that x takes plus infinity, then the CDF function should go to 1. So this is not being followed. So this is also not a valid CDF function for a continuous random variable. So there are three questions, question number 3, 4 and 5 in activity questions 4.4, which uses the same data. So we have been given the cumulative distribution function of a continuous random variable x. F of x is equal to 0 when x is less than minus 1. It is equal to half times x plus 1 squared when x is between minus 1 and 0. Minus 1 is included. And it's equal to 1 minus 1 by 2, 1 minus x squared, 0. X goes from 0 to 1 and it's 1 afterwards. So this is some kind of a CDF function that is given. In question number 3, we have been asked what's the probability that x will take value 0. So as we know, for any continuous random variable, the probability that the continuous random variable will take any particular value, it is always 0. So this is the answer for the third question. Coming to the fourth question, find the value of probability that x will fall in the range minus 3 to 0.5. So as you know, when we have to calculate that continuous random variable will fall between a and b, we can subtract the CDF at b and a and we can find that probability. So here we will subtract the PDF of minus 3 from the CDF at 0.5. So what is the CDF at 0.5? So this is the CDF function. We can easily use it to calculate the CDF. So between 0 and 1, this function holds. So 1 minus half times 1 minus 0.5, that is 0.5 squared minus CDF at minus 3. So before minus 1, the value of the CDF is 0, so it's just 0. So 1 minus 0.25 by 2, so it will be 0.875. So it is the probability that x will fall between minus 3 and 0.5. In the fifth question, we have been asked find the probability that x will take value greater than equal to 0. So as we know, we can find the probability of this as 1 minus probability that x will take value less than 0. So this is nothing but the CDF, 1 minus the CDF at 0. So we can use this formula to calculate the CDF at x equals 0. So it will be 1 minus CDF at 0 is 1 minus half times, when you put x equals 0, it will just be 1. So it will finally be half. So 0.5 is the probability that x will be greater than or equal to 0. So these are the questions 6, 7 and 8 from activity question 4.4. So these all questions use the same data. So here we have been given a CDF of a random variable x, and we have to find the value of probability that x will take value -2. So for the sixth question, we have to find probability that x will take value -2. So here we can see that there is a jump in the CDF function. So this function is not representing a continuous random variable strictly. Okay, it is a mixture of the random variables, continuous and discrete. As we can see here, the amount of jump is 0.3. So it means that the probability that x will take value -2, it is equal to 0.3, the amount of jump there in the CDF. In question number 7, we have to find the value of probability that x will be in the range 0 and 2.5. So we can see here that between 0 and 2.5, the function is a continuous function. So we will have to subtract the CDF at 2.5 and the CDF at 0 to find this probability. So we have to find the probability that x will be between 0 and 2.5. For that, what we need to do, we need to find the CDF at 2.5 and subtract the CDF at 0. So add 2.5 at this point and at 0 this point. What's the value of the CDF function? But we don't know what's the value here. We can guess, but that might not be correct. So the better approach would be to find the equation of this line and this line, and we will find what's the value of this line at x equals 0 and x equals 2.5, and that will represent the value of the CDF at those points, and then we will subtract them and we will be able to find the required probability. So we can find the equation of the first line as y minus 0.3 divided by x plus 2 is equal to 0.2 divided by 4. So it is 4y minus 1.2 equals 0.2x plus 0.4. So it will be 4y plus 0.2x plus 1.6. So this is the equation of this line. Y equals 0.05x plus 0.4. So as you can see, at x equals 0, the y coordinate of this line will be equal to 0.4. So the coordinates of this will be 0 and 0.4. For the second line, we can similarly find the equation of the line. So it will be y minus 0.5 divided by x minus 2. It is equal to 0.5 divided by 1. So finally we can write 0.5x minus 1 plus 0.5. So it will be y equals 0.5x minus 0.5. So the equation of this line is y equals 0.5x minus 0.5. So if we put x equals 2.5 here, what we will get? We will get y equals, if we put x equals 2.5, 0.5 times 2.5 minus 0. So it will be equal to y equals 0.75. So coordinates of this point it will be 2.5 and 0.75, right? So this is the CDF at this point 2.5. So now we can subtract these values, the CDF value at this point 0.75 minus 0.4, so it will be 0.35. So this is the probability that x will lie between 0 and 2.5. Coming to the 8th question, we have to find the value of probability that x will take value greater than or equal to 1. So here again we can write it in terms of the CDF at 1. So we found out the equation of this line. So we have to put x equals 1 in this equation of the line. So when you put x equals 1, y will become 0.45. So the coordinates of this line is 1 and 0.45. So the CDF at 1 is 0.45. So 0.55 is the probability that x will be greater than 1. This is question number 1 from activity questions 4.5. The probability density function of a random variable x is given in the figure. Choose the correct options for the random variable x. So this is the PDF of a random variable x. So the first option says that the range of x is between 0 and 1. Yes, that is correct, because the random variable x has non-zero PDF in this range, right? So whenever we are asked to find the range of a continuous random variable, we see at all the points where the PDF has non-zero value, and that is the range of a continuous random variable. So in this case, the first option would be correct. The second option says that the range of x is between 0 and 14, including both the points. So that's not correct, right? Because it's asking about the range of the random variable, right? Not the range of the probability density function. Yes, as a function, this PDF might have a range between 0 and 14, and I mean, it depends what kind of a function it is. But here we have been asked the range of x, and x has PDF non-zero between 0 and 1. So this is incorrect. The third option is saying that probability that x will take value 0.95 is higher than the probability that it will take value 0.2. So it is saying that probability that x will take value 0.95, it is greater than probability that it will take value 0.2. So if you look at the PDF function, here it's 0.2 and here it's 0.95. So it might look like it is saying correctly, but actually this is incorrect. Why? Because for any continuous random variable, as you know, even though the PDF function may be non-zero, but the probability that a continuous random variable will take any particular value, it is always 0, right? So the probability that it will take exact value 0.95, it is 0, and probability that it will take value x equals 0.2, it is also 0, right? So we cannot talk about the probability of a continuous random variable taking some exact value. So this option is incorrect, right? Coming to the fourth option, probability that x will take value close to 0.95 is higher than probability that it will take value close to 0.2. Yes, that might be correct, because whenever we are talking about a continuous random variable, we can only talk about the probability that the random variable will take values somewhere around that value, right? So at 0.2, we cannot talk about the probability, but we can talk about the probability that it will take values around here. So suppose we are talking about some small range around 0.2, and it will represent the probability that it will take values in this range. And around 0.95 also, we take a small range and we find the area. So it will represent the probability that it will take values in this range, right? So definitely this area will be higher than at this point. So it is clear also from the value of the CDF function. The value of the CDF function is higher at this point. So any area for any particular interval you find, around this 0.95, it will be higher than at 0.2. So yes, this is correct. These are questions 6, 7 and 8 from activity questions 4.5. So these have the same data. Consider the following probability density function fx of a random variable x. To answer the questions 6, 7 and 8. This function, this PDF function is equal to kx when x is in the range 0 and 1, not including 1, and it's 0 otherwise. We have to find the support of x. So as you know, the support of a continuous random variable consists of all the points where the PDF function had some non-zero value. So when you put x equals 0 in this PDF function, it becomes 0. There is one more thing, that this random variable is only taking some value, right? Assuming that k is some non-zero value, it is taking only some value very, very close to 1, but not at 1, because here there is no equality sign and it's 0 otherwise. So at 1 it should be 0. So the support of the random variable x is 0 to 1, but not including the endpoints 0 and 1. Question number 7, we have to find the probability that x will take values between 0.5 and 0.8. So we have the PDF function and we can easily calculate this probability by integrating this PDF function between this range 0.5 to 0.8, but we don't know the value of k. So what we can do here is we can integrate this PDF function, equate it to 1 and find the value of k. Then by putting k, we will be able to integrate it from 0.5 to 0.8 and find this required probability. So first of all, let's find k. Finding k. So when you integrate over the full range of the random variable x equals 0 to 1, k is a constant, so we can take outside x dx. So it will be k ax squared by 2. X will go from 0 to 1. So k by 2. And this integration, because we are integrating over the full range of the random variables, it should be equal to 1. So it means k equals 2. Now for finding this probability, we can put the value of k here and integrate this from 0.5 to 0.8. So 2x here dx. So 2x squared by 2, so it will just be x squared. We are integrating from 0.5 to 0.8. So it will be 0.64 minus 0.25. It will be. In question number 8, we have to find the value of f of 0.5, where f is the CDF of x. So we have to find the CDF of x at 0.5. So as we know, we can find the CDF of any random variable by integrating it from minus infinity to the point at which we have to find the CDF. What do we integrate? We will integrate the PDF function. So 2x dx. So instead of minus infinity, we can put 0 here, because the lowest value that x can take is 0. Actually, it cannot take value 0, but this does not make a difference, because the probability that a random variable will take any particular value, it is 0. So we can put x equals 0 here and integrate up to 0.5. So 2x dx. Finally, when you integrate, it will be 2x squared by 2. So x squared from 0 to 0.5. So it will be 0.25. So this is the CDF of x at 0.5. This is question number 2 from activity questions 4.6. We have been given a uniform random variable x. So x is uniform in the range a and b, including a and b. It is a continuous random variable. We have been given that the probability that x will take value less than or equal to a plus 2, it is equal to 0.2, and we have to find the probability that x will take value greater than or equal to b minus 2. This is unknown, we have to find out. So as we know, for any uniform continuous random variable which is defined between a and b, the PDF is equal to 1 by b minus a, and CDF capital F at x, it is equal to x minus a by b minus a. it is the probability that the random variable x will take value less than or equal to some small x. So we have been given here that probability that x is less than or equal to a plus 2 is equal to 0.2. So basically it is the CDF at the point a plus 2. So we can use the formula of the CDF for a uniform continuous random variable. It is just x minus a, the point at which we are calculating the CDF. So it is a plus 2 minus a, the lower limit, divided by b minus a. It is equal to given as 0.2. So it will be 2 by b minus a, which is 0.2. So b minus a is equal to 10. Now we have to find the probability that x will take values greater than or equal to b minus 2. So we can write it as 1 minus the CDF of x at b minus 2. So here in place of CDF we can substitute with x minus a. So b minus 2 minus a divided by b minus a, that is equal to 10, we know. So it will be 1 minus b minus a is 10 and 10 minus 2 is 8. So it will be 8 by 10, that will be 2 by 10 or 0.2. So this is the probability that x will take values greater than or equal to b minus 2. This is question number 3. The amount of milk produced every day by a dairy is uniformly distributed between 100 liters and 120 liters. What is the probability that the amount of milk produced is more than 115 liters, given that on that day more than 110 liters of milk was produced? This is question number 3. The amount of milk produced every day by a dairy is uniformly distributed between 100 liters and 120 liters. What is the probability that the amount of milk produced is more than 115 liters, given that on that day more than 110 liters of milk was produced? So first of all, let x represent the amount of milk produced every day by the dairy. So x is uniformly distributed between 100 liters and 120 liters. So x is clearly a uniform distribution, uniform and continuous between 100 and 120. And we have to find the probability that the amount of milk produced is more than 115 liters. So probability that x is greater than 115 liters, given on that day more than 110 liters of milk was produced, given that more than 110 liters of milk was produced. So this is the condition probability that we have to find out. So as usual, we will write it as the joint divided by the marginal. So we can write probability that x is greater than 115 and x is greater than 110. And in the denominator, we will write the margin probability of the event on which it is conditioned, x greater than 100. So talking about the joint probability, when x is greater than 115 and x is greater than 110 both, then we can directly write it as x greater than 115 because it is greater than 110 also, and here x greater than 110. So this can be written as 1 minus the CDF of x at 115, and this can be written also as 1 minus the CDF at 110, the probability that x will take values less than or equal to 110. So since this is a uniform and continuous random variable x, we can use the CDF formula for uniform and continuous random variables. So for uniform continuous random variable x, we already know that the CDF at x is given as x minus a divided by b minus a, when our x is uniform in the range a and b and it is continuous. So here we can use 1 minus, what will be the CDF at 115? It will be x minus a. x is 115 here minus 100 lower limit divided by b minus a, that is 20, and here 110 minus 100 divided by 20. So it will finally be 20 minus 15, that is 5 by 20, and here it will be 20 minus 10, that is 10 by 20. So this is 1 by 4 and this is 1 by 2. So finally we will get 1 by 2, 0.5. So this is the probability that x will be greater than 115 given that x has already taken value greater than 110. In question number 6, we have been given an exponential distribution x. We have to find the value of probability that x will take values in the range 3 and 5. So x is an exponential distribution with the parameter 2, lambda equals 2. And we have to find the probability that x will take values in the range 3 and 5. So as you know, for finding this probability, we can integrate the PDF of x from x equals 3 to x equals 5. So as you know, for any exponential distribution with the lambda parameter, the PDF is equal to lambda times e raised to the power minus lambda x. So here we can integrate from x equals 3 to 5. The PDF is 2 times e raised to the power minus 2x. So 2 we can take outside. Lambda is given as 2. E raised to the power minus 2x dx. When you integrate it, it will be minus e raised to the power minus 2x between x equals 3 and 5. So it will be minus e raised to the power minus 10 minus e raised to the power minus 6. So that is finally e raised to the power minus 6 minus e raised to the power minus 10. So this is the probability that x will take values in the range 3 and 5. So the option corresponding to this answer is the third one. In question number 8, we have been given a random variable x which follows a normal distribution with mu equals 50 and sigma squared is equal to 100. We have to find the probability that x will take values in the range 45 and 62. So x is a normal distribution with mu equals 50 and sigma squared is equal to 100. And we have to find out this probability, x taking values in the range 45 and 62. So what we can do is first we can standardize this random variable x and then find the probability in terms of the CDF of the standard normal random variable. So for standardizing this, as you know, what we do, we subtract the mean of the random variable x minus mu is given as 50 divided by the standard deviation. So sigma squared is equal to 100, so sigma will be 10 divided by 10. We will do it on all sides. So 45 minus 50, that is minus 5 by 10, that is minus 0.5 on the left side, and on the right side we will have 62 minus 50, that is 12 by 10, that is 1.2. So finally we can write it as the CDF of the standard normal distribution at 1.2 minus CDF of the standard normal distribution at minus 0.5. So this is the probability that x will take values between 45 and 62 in terms of the CDF of the standard normal distribution. So the option corresponding to our answer is the fourth one.